basically, as I mentioned earlier, it's the continuation from what we have learned previously. We learn about converting our system into a state-based model, and we try to continue what types of state-based model we have. Do they have? I mean, in state-based model itself, we can also represent it in a few types. All right. Like this is what I mentioned just now. Um, what we try to do is we try to have a look at a signal flow graph. Okay. Before we get into the signal flow graph, we try to convert our system from a function, and of course, maybe from state space into system type of function as well. Uh, and later on, or at the same time, we also will look at various form of state space representation, where here we have a phase variable form, cascade form, diagonal form, Jordan, controllable, canonical form, and also observable, ob- observable, susah nak cakap, canonical form. Anyway, with respect to this course, we only tackle these two rate form, which is phase variable form and also controllable canonical form. So the rest will be introduced to you, but not what you call it, not being asked in your assessment. Okay, this is we review back what we have learned in previous chapter. We learn about state space model where it involves two equations, which are uh, state equation and also the output equation. The state equation given by x dot equals to ax plus b u, or you can always rename it in whatever notation that you like. Maybe here I have ax plus bb, and for the output equation we have cx plus du, or in this case I put it as dv. And you also learn about how to represent these two equations in terms of a block diagram. So here is the block diagram for this kind of or for this state space model. And and also we learn about each of the elements inside our state space model. For example, we have A, B, C, and D considered our matrices, model matrices. Maybe it will represent our system, it will represent the output, and also output of our state space model. And we also have a column vector over here, which is x of t, where x normally known as our uh, state vector. It's a column vector, n times 1 column vector. Depends on the degree or the order of our differential equation, or order of our system. And also we have V, or sometimes U in previous lesson. We learned that this part is V times U. So U is basically our input vector. Also a column vector in this case. All right. Alternative representation in state space. So I think we can read through this slide, why we um, have various types of formation of state space model. So here is the reason, or so here is the answer for that question. Here we have phase variable, cascade, parallel, controller canonical, also observer canonical, and why we need that. So the answer is representation due to different physical meaning. Maybe we need to, it's easier if we have that particular form of state space model, and also it leads towards the ease of our analysis, especially when we try to uh, get the solution of our state space equations. Okay, I think I will try to skip this one. This is basically a transfer function turned into a state space. Of course, from transfer function into a state space, first we need to consider our differential equation, and we can convert from a transfer function into a differential equation. Of course, from differential equation also we can convert it into transfer function. But if we have a transfer function and we try to convert it into a state space, first thing we need to consider is we need to consider converting the transfer function into a differential equation. So here is how we do it. And while we convert from transfer function into a differential equation, we must note it that that kind of procedure will lead us to a form of state space model which is known as a phase variable form. All right, this is the way we convert it. And right, I will try to, it is easier for us to see the example of how do we form a phase variable state space model. Okay. I will skip this one. Maybe this is a bit difficult to understand on the procedure to convert from transfer function into a phase variable state space form. Okay, let's say we have a transfer function like this. We have 24 s to the power of 3 plus 9s squared plus 26 s plus 34. So this is considered our transfer function. And we have our system input, which is R of S, and system output, which is C of S. So the first thing we need to do is we need to determine the differential equation. Here DE means differential equation. And to do that, it's very easy. You just cross multiply this the elements. So in the denominator side, we have S to the power of 3. We try to um, switch it into our left hand side, and for R of S, we switch it into right hand side. So with if you do that, it will lead to this equation. We have S to the power of 3 blah 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 times C of S equals to 34 R of S. So this is considered our uh, differential equation, where if you try to expand this equation, it will lead you into this equation that we found below. We have T triple dot, or 3 C cube dt cube. We have 9 C squared dt squared. We have 36 C C dot, and also we have plus 34C. This will happen when we try to expand this equation. And please note that before you expand, you also would have to consider inversing the Laplace and consider a zero initial. So what we see over here, the S operator over here as a Laplace operator S has been disappeared, and what we have T triple dot plus 9C double dot plus 26 dot plus 24 C um, equals to 34R. So the operator, Laplace operator here has been disappeared, or we inverse this equation to be in the time domain. All right, later on, um, we try to define our each of these terms in order for us to setting up or construct our state space model. The first thing that we need to consider is we try to take our first state. Okay? Our first state x1 equals to c. And before we get into this, before I forget, that if we have a third order differential equation over here, for example, we have c triple dot, meaning that our state will be, we will have three states, x1, x2, and x3. The first one we need to define is that c is considered as x1, and we take the derivative of c and consider it as x2, and we take the derivative of x2 or second derivative of c and consider it as x3. And with that, we later on will um, differentiate or take the derivative of what we define in the first place. So here we take the derivative of x1, x2, and also x3. Taking the derivative of x1, we will end up with x1 dot. So here, maybe the words or what it's call it, the equation here is not that clear, so I put it as x1 prime, or here also known as x1 dot. So I try to represent this x1 dot into x1 prime. So these two are basically the same. So when we try to when we differentiate the definition that we defined earlier, this x1 will become x1 dot, and x2 will become x2 dot, x3 will become x3 dot. And by taking the definition of what we have previously, we know that x1 dot is basically x2, because x1 is c, and we take the derivative of c is dc over dt, and dc over dt is basically the same that we found earlier, which is basically x2. And x2 dot is the second derivative of c, and second derivative of c is basically x3. And the third one is x3 dot is the third derivative of c, so this is c triple dot. And with this definition, we will see that x1 dot equals to x2, x2 dot equals to x3, and x3 dot is basically will lead us to this equation. And we know that this x3 dot minus equals to negative 34 times 1, sorry, negative 24 x1 minus 26 x2 minus 9 x3 and plus 24r. So basically, we try to rearrange this equation back to get our x3 or or the c triple dot. All right. And with that definition, okay, you see here we simplify what we have previously. So with these three differential equations, it is easier for us to set up our or to construct our state space model. Now we have in our state space model, we know that of course we should have the we have x dot equals to ax plus du. Okay, and this x dot is basically these three elements. X1, put it over here. X dot is basically a column vector consists of x1 dot, x2 dot, and also x3 dot. For x is also a column vector, which is the our state vector. Okay. And this is our A, and of course this is our B. And in this case, this R is 1 times 1 matrix. All right. Looking at these three equations, it's easier for us to set up this equation. And the first one, if you look here, x1 dot equals to 0 times x1 plus 0 times r. The next one is x1 equals to 1 times x2, because we know that x1 is equal to x2. Okay. So that's why we put it 1 over here. And the rest, we have x1 equals to 0 times x3 plus 0 times r. And for x2 equals to 1 times x3, because we know that x2 is equals to x3. And the rest of the element should be equal to 0, because we don't have any other element beside except x3. And okay, this is very crucial. The third one is x3 dot. And if you go through this equation, you might find that the element really translate from the equation that we have over here. So x3 dot equals to negative 24 times x1. This is the first element. First element over here. Times x1 plus negative 26 times x2. So negative 26 times x2, we have it over here, plus negative 9 times x3, and this is what we have in the third term, and plus 24 times r. Okay, then we finish putting all the elements of the differential equation into our state space model. Okay, we done with our state equation over here. We have x dot a times x plus b times u. This is considered r is considered our u lah in this case. Alright, we done with the state equation, and for the output equation, remember that the output of our system, okay, if you look over here, the output here is considered as C of S. So where is our output? Basically, our output is x1 over here, or our output is basically C. Now, if you look at our output equation, we have y equals to C times x plus du. And of course, you can neglect this term due to we don't have any disturbance or input related matrix in our output. So we only consider this part, and please remember that this x is basically a column vector consists of three elements. We have x1, x2, and x3 arranged in a column manner. So the output that we would like to have is y equals to C. and we can put it as y equals to x1. So that's why over here, or at the output equation, we only have x1, y equals to x1 plus 0, x2 plus 0, x3. So we done with our output equation at this stage. Right? And to build the block diagram, so this block diagram, the first one, we need to know that we should have one summation point over here. And this one summation point later on will be connected to three integrators. The first integrator, which is basically over here, we know that our equation, we have x3 dot equals to blah 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 blah. So here we have x1, maybe we have x2, and also x3. So these three states will sum together. So that's why we see here the summation is located over here. And if you integrate x3 dot, you will end up with x3. And if you integrate x3, basically this x3 is also known as x2 dot. Okay, you should refer the definition that we have earlier. And if we integrate x2 dot, it will lead us to x2. And basically x2 is also can be written as x1 dot. And if we integrate x1 dot, it will lead us to x1. And of course, x1 is basically our output that we desire. And this 9, this 26, and this 24 is basically a multiplier. And you can also do something which is like this as well. Put it as plus over here. Both all element is plus in a plus sign. Over here you put negative sign. So that kind of block diagram or that kind of drawing also acceptable in order for us to come up with the block diagram of our state space model. And if you look at equation that we have for x3 dot, x3 dot also not only consists of the state, but it also consists of element of our input, which is r over here, and multiplier for r is 24 in this case. So basically, this block diagram is coming from the equation that we see over here. Maybe this is not clear. Okay, maybe I would say that the equation coming from this equation. Okay, we have x3 dot equals to negative 24 x1, negative 26 x2, and so on. All right, that's the first one. And the second one is, what if we have a polynomial in the numerator side, meaning that before this we only have a constant over here. We have 24 located at the numerator side, and in this case we have a polynomial for our numerator element. So what if we have that kind of transfer function? Okay, if you have that, you come across with that kind of transfer function, what you need to do, you need to separate the numerator and denominator into two blocks. Okay, the first one, of course, we try to cater the denominator first, and later on we try to cater the numerator polynomial. Okay, and the steps is almost the same with what we see previously. Okay, let's see the example. All right, let's say we have a polynomial which looks like this. We have s squared, sorry, not polynomial. We have transfer function, which is look like this. We have numerator with the polynomial, denominator also with the polynomial. S squared plus 7s plus 2 divided by s cubed plus 9s squared plus 26s plus 24. Remember that this is our input R of s and this is our output C of s. And the first one, the first thing that you need to do is you need to separate the system. The first block over here is considered our denominator, and the second block here we consider as our numerator block. Okay, for the process, I think the same as we've seen earlier. The first one, we need to do some cross multiplication. Okay, before we get into the cross multiplication method, if you divide those two numerator and denominator blocks, you need to label the output of the first block. So in this case, it is labeled as x1 of s. Maybe you can also use another notation, maybe m also can, maybe, because in our state space model, we will come across x1 again. So to avoid confusing, maybe you can label it with m of s. I don't know, maybe not c, maybe what else? T of s, maybe maybe T of s also can over here. But anyway, if we have our solution like this, let's go through the solution first, and later on we see how we change what elements should we change if to avoid confusion. All right. Here we have R of s and as the input, and the output the x1 of s, and this is considered our first block, and we settle this first block first. We solve this one, and again we try to apply cross multiplication. If we do the cross multiplication, we will end up with this equation. We have x1 of s, s cubed plus 9s squared plus 26s plus 24 equals to R of s. And we do some assumption, or we try to define our state first. Okay, if you look over our transfer function over here, we have the highest power here is s to the power of 3, and we should expect that our state, or the x over here, should be a 3 by 1 column matrix. In other words, we're going to have 3 states in our system. Sorry, this is x2, x3. We're going to have 3 states because the highest power over here is s to the power of 3. And first we define our state. So this is what I try to avoid. Here, if you look at here, we have x1 equals to x1. So if we use a different notation over here, let's say we put it as m. Okay, okay. x1 equals to m, and x2 equals to m dot, and x3 equals to m double dot, and x3 dot equals to m triple dot. And the equation over here will looks like this as well. We have m triple dot plus 9m double dot plus 26 m dot plus 24. Yes, Lynn. Yeah, you're correct. What I try to do here, I try to avoid the confusion. So I try to replace this x1, okay, with capital X1 into a capital M to avoid confusion. Because if you see over here, later on you will have x1 dot, x1 double dot, x1 triple dot. So that's, I think, a bit confusing at this stage. So what I try to do is I try to replace this x1 or capital X1 into a different notation. So here maybe we select M for x1 of s. So here I finish the equation, yeah, equals to okay, no, I should, because x1, this is M, okay, 24 times M equals to R. Okay. This is basically our equation based on what we have over here. Okay, based on what we have. So if we look at the original solution, maybe you find that x2 is equals to x1 dot, x3 is x1 double dot, x3 dot is x1 triple dot. Right. Whichever that you prefer, but I think to avoid confusion, maybe we can change the notation of our output of the first system. Basically, we can define any of notation that we like over here, and to make it to avoid the confusion, maybe we try to use a letter which is not gonna be not have double meaning in our system. All right. So we know that sorry, m is x1, m dot is x2. Okay, and you can change this equation into one that we define over here. Okay, we know that this m3 dot is sorry, and not m3 dot, m triple dot is x3. Okay, based on this definition, and this 9 m double dot basically is x3, so we know that 9x3, and 26 m dot is x2, so that's why we have 26 times x2. 24 m is basically our x1, so that's why we have 24 x1 and equals to r. So from this equation, rearrange this equation, and we have the equation of x3 dot, or this is basically m triple dot. Okay, written in the form of x3 because we try to put it into our state space model over here. And of course, for our state space model, again, we consider x dot equals to ex times bu, sorry, plus bu. Okay, and x dot over here is basically, if you consider this is the dot, x1 dot, x2 dot, x3 dot. Okay. X is also a column vector, which is x1, x2, and x3. And R is a one by one input matrix. Okay, how do we put this equation into the model? The first one, we have x1 dot equals to 0 times x1 plus 1 times x2 plus 0 times x3 plus 0 times r. So we know that x1 dot, okay, here, is basically our x2. Okay, x1 dot, or in this case we have m lah, m dot and double dot and triple dot. And for x2 dot is basically this multiply with x3 only. Okay, and for x3 dot or m3 triple dot, basically we try to put all this information, all these terms in the last row of our A matrix. So negative 24 times x1. I think this should be a negative sign. Okay. Because if you put 9, 26, and 24 towards the right hand side, this should be a negative, negative sign. Alright, negative 24 times x1, negative 26 times x2, negative 9 times 3, plus 1 times r, because we have r over here. Alright, by setting up this state equation, this is known as phase variable form. Okay. Later on, I will show you the pattern of phase variable form. Okay, now we get into our second block, which is the numerator, consists of numerator side. So here we have earlier, let's see what's this. Okay, we done this part, the first block, and we try to analyze this, the other block, the second block. So the input of this block is x1 of s, and the output is c of s. And if you label it as m, maybe the input here is m, the output is c. So now the x1 over here, you can also put it as m as well. Okay, and again we try to cross multiply, and when we cross multiply we will end up with this equation. C equals to s squared plus 7s plus 2 times x, or x1, or this is also can be seen as m of s. And based on our definition that we have earlier, we have m equals to x1. Okay, and m dot equals to x2, and m dot, but I put it as m double dot. M double dot is considered as x3, and is x1, of course x1. This is x1 dot, and this is x1 double dot, or x3 for our state. All right, by using this definition, we try to substitute this definition into our equation that we have over here. If you expand this equation, you will have c equals to x1 double dot plus 7 x1 dot plus 2 x1. Okay, and referring to this definition, we have x1 double dot is x3, or maybe m double dot over here is x3 plus 7 x2 and plus 2x1. Okay, maybe this uh, equation is not quite right. This should be 2x1. Okay, so that's how we convert from we solve the second block using the definition that we defined earlier, and of course we need to compare it with our differential equation of the second block. So using this equation, okay, we will come up with our output equation, which is y equals to tx plus t times u. Looking at the equation itself, we don't have this element. So our output here is y equals to cx. And if you look back at this block, the output here is c. Okay, c. Yeah? And here, where's the c? So the c here is based on equation that we have here. So write down this equation in matrix form. In other words, I would say. So in matrix form, we have y equals to, we don't know what is the dimension of this matrix yet, but we know that this is the matrix of our state or x. And if we like to have this equation translated into a matrix form, meaning that this will be also a row vector consists of 1 times 3 row vector, because we know that y equals to 2 times x1, okay, plus 7 times x2 plus x3, 1 times x3. So that's how this equation can be formed. Sorry, this yeah, equation in matrix can be formed. All right, and later on, if you try to put it into a block diagram, okay, if you see over here, the one that we have at the bottom here up until here is basically based on the denominator side. Denominator, deno, and the one that we have at the top over here, okay, is basically representing the numerator side, or numerator side of the transfer function. Okay. Now, any question? Guys, any question?
Ya doktor, ada yang CS over X1S tu yang belakang equation S square plus 7S plus 2, dia belakang S tu maksud dia apa?
Oh, this one. You mean
Ya.
this one? Okay. This is operator, Laplace operator, meaning that it's in
Doktor,
Laplace domain.
yang atas punya.
This one.
Ah,
Okay. Oh, maybe we missed something over here. Oh, okay. Basically, this is a Laplace operator. Suppose that this one can be
supposed to be
neglected.
X1S kan?
Yeah. No,
Oh,
not x1s, because x1s is over here.
Uh-huh.
Okay, this one can be neglected. This should not be here.
It should not be here lah. Oh,
Hmm.
okay. Okay, macam tu. Okay lah, faham.
Yeah. All right.
Terima kasih doktor.
Based on the, yeah, of course, we don't have the S operator over here. All right. Can I proceed? Okay, this is what I would like you to do. For exercise 1, have a look at the example that I showed you earlier. Maybe the second example is very helpful in order for you to solve exercise 1, where in exercise 1 we have polynomial at the numerator side, and we have the denominator side. I think the highest power should be s to the power of 3. And of course, by looking at the transfer function, roughly I would say that we're going to have 3 states. We have x1, x2, and x3 as formed as a column vector. All right, this one I put it as exercise for you guys to solve it later on. All right, now we get into our signal flow graph. Okay, before we get into our signal flow graph, uh, I'm about to say signal flow graph. Signal flow graph. Okay, signal flow graph. Before we get into that matter, if you look over here, there is a pattern that very similar that we looked earlier in example 1. Over here, on we have a diagonal matrix 1 1, and down here we have all our elements based on the transfer function. All the information is stuffed it at the last row or the third row of the state space model. If you look at example 1 or so, it is the same. If you see here, there is a diagonal matrix over here, and also all the information based on the transfer function differential equation, and of course from the transfer function, is located or being stuffed at the last row down here. Okay, this kind of setup or metric setup is known, or the state space model over here is known as a phase variable form. Okay. Now get into the signal flow graph. Okay, signal flow graph is basically the same as what you seen in your block diagram. It's basically the same over here, except that it is presented in a more simpler way in terms of on the lines and also circles representing the integration. All right, the states and as well as the derivative of the states. Okay, maybe I'll skip this one and get into the example for easier understanding. Right. Let's say we have this kind of differential equation. We have 3 differential equations: x1 dot, x2 dot, x3 dot, and if we have these 3 equations, okay, basically we can put it in a state space model where we have ax plus bu. Okay. X over here is a 3 by 1 column matrix. Okay. And of course for x, we have also a column matrix of x1, x2, x3, and for u, okay, we don't have any R1, R2, R3, meaning that it's a 1 by 1 input matrix, 1 by 1 matrix, only R. And we can write down all these three equations in a state space form. But in this case, what we try to do, we try to from this equation, we try to draw or sketch or construct the signal flow graph or SFG. So that's a step of doing that. The first one, we need to identify three nodes to be three state, not state lah, state lah here. Three state variables, which is x1, x2, x3. And how do we know that this is we have three state variables? It is based on the equation that we see over here. And three, first we identify the nodes and three nodes left of each of the derivative input derivative, and three nodes left of each for derivative inputs R and output 1. It's difficult to understand based on this description. I would say that first we know that we have three states. So meaning that we're going to have the first one, we try to draw this 1, 2, 3. These three pairs. Okay. These three pairs with lead us to, this is known as x3 dot, and next to it is the derivative of the integration results of x3 dot, which is x3, and this is x2 dot, and next to it is x2, this is x1 dot. And from this block, okay, from this x3 dot, we take draw a line over here. Okay. We draw a line here, and we know this line will represent the integration action, integrating action, the 1 over s. The 1 over s is basically same as when you try to integrate. So the integration is represent as 1 over s. This is what you will do at the moment. First, you draw these three pairs because we have three states over here. We know that we're gonna have three pairs and connect each of the pairs, and the relationship between each of the elements in each pair is integration or integrating action, or 1 over s. And at the left and right, far right and far left of these three pairs, we will put our input and also our output circles over here. So that's what we're gonna do first. Okay, this is what we have. Now, interconnect the state variable and their derivative with the defining integration 1 over s. So 1 over s, as I mentioned earlier, is our what do you call it, integration. Okay, step number 3, we try to go one by one of our state equation here. And the first one, let's say we go into the first equation. We have x1 dot vi drop this one first. this is from the actual equation. X 2x1 minus 5x2 plus 3x3 plus 2r. So this definition is coming from the original differential equation of x1 dot. So from here, we know that x1 dot, where is our x1 dot? x1 dot is over here, and it will receive 2x1. So you draw a line, circle over here, and label it as 2. And no need to put an positive side, because we know without any sign over here, it's considered as positive. And make sure the arrow is going in one dot. And the second one is negative 5x2. So where is our x2? x2 is over here. Okay. If you look at the original drawing, x2 is here, x1 is next to x1 dot is next to x2. So just draw a line over here, and this is the line that I mentioned. Now, okay, put an arrow towards x1 dot and label it as negative 5. For the third term, we have 3x3. So we get into x3 circle over here and draw a line towards x1 dot and put the value as a positive value of 3. So no need to put positive over here, because we know without any sign, the element should be a positive value. And the last one is 2r. 2r means that we go into r point, circle of r, and draw a line towards, we draw a line towards this x1 dot. Then don't forget to put an arrow to it. Value here is 2. So that's how we draw the connection of first differential equation. And we will do this for the rest of the equation that we have. So the second equation, which is x2 dot, now we focus on x2 dot and draw a line to it. And the third equation, we focus at x3 dot and we draw a line to x3 dot. And the same procedure that we did earlier for x1. And the last one, okay, the last one is the equation that I didn't mention before this, which is the output equation. And the output equation is y. And remember, at the end, at the farthest right hand side, we have circle which labeled as y of s. So if we have equation of y equal to blah 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 blah, meaning that we need to draw a line which represent that equation. So here we have y equals to negative 4x1. Where is negative 4x1? We know that next to y is x1. So we draw a line from x1 to y and put an arrow to it and put it as negative 4. We have 6 plus 6x2. So here is x2. We draw a line, the semicircle over here, and put an arrow to the line and put the value as 6. And finally, this 9x3, and find where is x3. So here is x3 and draw a line to point y and put an arrow, label it as 9. Okay, that's very easy, I think, for a signal program, how we draw signal program. And this drawing is, I think, easier compared to what we have in the block diagram, where in block diagram, you need to do several blocks, and the block with integrator, like something like this, is a bit messy compared to what we have for signal flow graph. Although you see here is a bit messy compared to what we have in the block diagram, but please note that this um, signal flow graph coming from a complex equation which looks like this, not as what we seen earlier in our block diagram. So that's how we draw the signal flow graph. And this signal flow graph basically is another way to represent our system other than using a block diagram. All right, now we finish with the first one, which is the um, space variable form. We move into our second form. I will not go into details about this form because we will not tackle this form in our assessment and also in our test of final. What I try to highlight here is that the form itself, the pattern of parallel form. If you see here, let's say we have a transfer function like this, and the process of getting into a parallel form representation of our state space is um, it will use a different procedure compared to what we seen earlier. The first one here for parallel form, we need to cascade each term. So here we see we have cascading. It's a bit difficult compared to what we seen earlier. And if you cascade this transfer function, and if this transfer function has been looked like this, I think the advantage of using this parallel form is to write this or to write this equation in terms of a time domain, and finding the solution of the uh, state space or for the transfer function is a bit easier if we try to cascade. But uh, the thing is that although it sounds easy, but it's not that easy, believe me, because if this is a polynomial, you need to know what is the combination of this. And sometimes the combination could be a complex number as well. So it's not that easy as you see over here. And another important thing about parallel form, the way we draw the signal flow graph is a bit different from what we've seen earlier. So we have a three parallel form, which is this is the pairs that I mentioned earlier. First, we draw pairs of our states, x1 dot, x2 dot, and x3 dot, and the pairs is arranged in parallel form. So I think I'll try to skip this one. And the representation of our state space is a bit different, where we have a diagonal matrix over here in parallel form, and we have all the elements of our input stuff in the input term. So that's the difference between what we've seen in phase variable form. So in conclusion, we say that a parallel form, we're going to have a diagonal matrix. And this parallel form also known as a Jordan form. So we're not going to get into details about this parallel form because not going to cover in your assessment. Okay, we get into our second exercise. Okay. In this second exercise, you don't need to answer this part. Only answer part A. Okay, remember? Only answer part A. No need to answer this part because it's not being covered in our course. All right. And to answer this exercise, I'll give you tips. The first one you see here, this is a a feedback system. And remember, our input is R of S and our output is C of S. Okay, the first thing you need to do is you need to come up with uh, a closed loop transfer function, C of S, R of S. No, R of S, C of S. Okay. No. C of S over R of S. You need to come up with this transfer function first. And to get the transfer function, you need to solve the closed loop transfer function first. Okay, closed loop transfer function. This closed loop transfer function has been taught or you have been taught earlier in this course as well as in your control system course. Or if you don't know how to come up with closed loop transfer function, please have a look at normal nice book to get the closed loop transfer function of a unity feedback. The first one, you need to get this closed loop transfer function before we can get into the representation of a system in phase variable form. So that's the tips for the exercise 1. Exercise 2. And exercise 3 also the same, where here you don't need to answer this question, only answer this one. That's enough. So again, this is also a unity feedback system. You need to find first the closed loop transfer function. Okay, and based on what I've seen over here, maybe you're gonna have 5 states, or maybe 5, maybe 4, maybe 5th order or 4th order. I'm not sure because you need to find the closed loop transfer function first, and later on you will get what is the numerator and what is the denominator of your system. Okay, that's the third exercise. Okay, any questions so far? Before we move on into our last bit, which is controller canonical form. Any question?
So far okay, boleh ikut.
Alright, thank you Bun for your response.
So far, so good, Doctor.
Okay, Brian, thank you. It's not that difficult, but you need to do it slowly lah. One by one, follow the procedure that I showed earlier. It's not that difficult. Just like playing puzzle. Puzzle. Yeah, puzzle. Filling out the blank space, something like that. All right. Okay, we move to our last part, last bit of this topic, which is the controller canonical form. Okay, can you hear me? I think my connection.
Yes, Doctor, boleh dengar.
Okay, my connection just now have some issue. I don't know. Okay, if you can hear, then we shall proceed. All right. Okay, for controller canonical form, it's more likely the same as what is seen in phase variable form, except that in controller canonical form, if you go through the statement over here, we try to obtain by reordering the phase variable form in reverse order. So it's easy. If you know how to come up with a phase variable form, meaning that for canonical, controller canonical form, just reordering uh, the phase variable form. But sounds easy, but not that easy. It's, of course, you need to follow all the steps. Let's say this is our transfer function, okay, and this is our phase variable matrix form. And in phase variable matrix form, as I mentioned earlier, we have a diagonal matrix over here. The element is 1. And all our information of denominator part will be located at the last row of our A matrix. And our output matrix, okay, not our output matrix, our input matrix, which is matrix B. In phase variable form, we will have element of 1 at the last row of our column matrix B over here. And for the output equation, depends on the types of transfer function. If we consider this transfer function, of course, we have denominator at the, we have numerator, polynomial numerator in the form of polynomial. So if we have a polynomial at our numerator side, meaning that we're gonna have matrix C, which is written like this, or written as a row vector uh, for matrix C over here. Okay, this is considered, or this form is known as phase variable form. Okay, for controller canonical form, as I said just now, we try to reorder this phase variable form. So how do we reorder it? Okay, the first one, the first step, of course, derive this transfer function into a phase variable matrix. The second step is we try to renumbering the phase variable in reverse order. Okay, let's say this is the phase variable form. Okay, this is our one that we have before this in previous slide. Let's say I put it as phase variable form over here. Okay, we try to renumbering the phase variable in reverse order, meaning that at the top here we have x3, down here we have x1. Okay, same goes to this matrix. We have x3 at the top, x1 at the bottom. Of course, in the middle we are gonna have x2 lah. Okay, and we haven't do anything with our uh, elements over here. Okay, we keep it intact. Okay, same that we have over here. Okay. The first step is only this red box. We renumber all the phase variable in reverse order. Okay, and the second step is rearranging in ascending numerical order. Rearranging what? Rearranging the elements, okay, in ascending order. Maybe I put it color. Green lah. Okay. You see here, this is the original arrangement of using phase variable form. 9 over here, switch it to the left, and followed by 26, and this 24, switch it to the right. Okay, we switch to be all the element to become like this. And another switch that we, another modification that we did is that these elements supposed to be appeared at the top of our matrix A. Okay, top row, the first row of matrix A. And before this, in phase variable form, we see that the information of our denominator appears at the last row of our matrix A. But for controller canonical form, first we shuffle or we switch sides, and later on we put it at the top of matrix A, the top, the first row of matrix A. And another thing that being modified or being changed a bit is the location of this diagonal matrix. Okay, this diagonal matrix will appear over here. Okay, and also the value of the elements inside our B matrix or our input matrix also will be moved into the first row of B matrix. So that's the thing that you need to um, consider first in the state equation. For the output equation, okay, originally we have 271 as arranged in this manner. So we did the same where we try to shuffle this element, okay, put it at the right hand side, and this element shuffle it to the left hand side. So that's what we have over here. And of course, this 7 is still over here because it's in the middle. All right. Now, the one that you see in the matrix down here on is known as controller canonical form just by rearranging the base variable form. Maybe now you're still in a cloud, maybe not quite understand or not quite familiar with the shifting and also with the, the shuffling of pieces of elements. I will give you guys time to um, get back into this example and find how do we and learn how do we convert from base variable form into a controller canonical form. And if we have this space model, we can easily write the differential equation based on the matrix setup that we have over here. For example, okay, for example here, let's say I consider the first differential equation, which is x1 dot is equals to negative 9 x1 minus 226 x2 minus 24 x3 plus r. Okay, so this equation coming from the solution of these elements. Okay. For the next differential equation, maybe in this case I have x2 dot over here is given by x2 dot equals to x1. Okay, x1 plus x1 plus 0 plus 0 plus 0. So x1, only x1. For x3 dot, x3 dot, basically I'm looking at this element, this element, this element. And x3 dot is 0 times x1, 1 times x2. And 0 times x3 plus 0 times so x2, only x2. So we will have three differential equations over here. The first one is based on the first x1 dot. The second one is based on x2 dot, which is x2 dot. And the third one is x3 dot. And based on these three differential equations, you can come up with a signal flow graph, which looks like this. Okay, and to compare it with what we have in for signal flow graph using phase variable form, you see here the pattern is the same, except that okay, the last part over here for signal for phase variable form is x1, and the last part over here before the output is x3, and the first one over here is x, this will be x1 dot, this is not x1 dot, x3 dot, this is x3 dot, and this is x1 dot. Okay, the circle before after our input is x3 dot, and the circle after our input for canonical form is x1 dot. So that's the difference. But if you look at the arrows, the values, it's almost the same. It's the same actually. It's not almost. It's the same, except for the location of our states over here has been shuffled. All right. In conclusion, we can say that phase variable form and controller canonical form, the coefficient of characteristic polynomial in the bottom row and the top row respectively. It means that for phase variable form, okay, characteristic polynomial will be at the bottom row. For canonical characteristic polynomial or the denominator coefficient will be at the top row. And second one, the system matrix that contain the coefficient of characteristic are called companion matrices to the characteristic polynomial. I think this is not as crucial as what we see over here. Maybe this is part of the definition, but the thing that's very crucial is that canonical characteristic polynomial will be at the top row, and for this variable characteristic polynomial will be at the bottom row. This is very crucial to differentiate between differentiate between phase variable form and controller canonical form. Okay, we have get into exercise number 4, and you are lucky over here. I have the solution, meaning that you don't have to answer by yourself. Maybe you can have a look at the solution as well to get what is the how do we convert from to be in the form of controller canonical form. Okay, any question? Oh, okay, solution is not complete. Is it complete? Yeah, it's complete, but maybe you can have a go through this solution based on the question that we have over here. If I were you, I will from this equation, from this sorry, not from this equation, from this question. First thing, I will convert it into fixed variable form, and later on, following the procedure of shifting, shuffling, something like that, I will represent the system in controller canonical form. I think this solution is a shortcut if you really understand on how to um, do the shuffling without any um, state space model metrics. Maybe it's okay, but if you don't know how to do that, this is without the matrices, state space matrices. If you don't know how to do that, maybe the better solution, I think the better option that you have is first convert into a phase variable form and later on represent the system in canonical form. Okay, in summary, okay, we in the towards the end of our session, we get into the summary. Um, let's say if we have a transfer function which is given like this, C of S, R of S, with that value of numerator and denominator. So this is sort of the difference of um, you will see uh, by having a various form of state space representation. And of course, with different form, the signal flow graph diagram as well as the um, block diagram will the way it's sketched or the way it's constructed it will be a bit different. For example, this is let's say like a default one lah, phase variable form. So the phase variable form, you see that you will have a block diagram, sorry, not a block diagram, signal flow graph diagram, something looks like this, and state equation, which looks like this, where we have a row at the bottom, which will present the characteristic polynomial or the denominator sides of our transfer function. And for controller canonical form, although the pattern of signal flow graph is almost the same. However, if you look at the states that we define over here, okay, the circle that we define over here we have x2, and over here we have x1. So it's been shuffled. The places have been shifted, shuffled with respect to each other, x1 and x2. In this case, we have two states, so x1 and x2 lah. And the most important thing that we notice that for controller canonical form, we have all the elements at the top side of our matrix A. I mean, the top row in matrix A. And if you try to find the equation of find back the equation of our system, it is based on the top row of our state space model. And if you look at the parallel form, it's almost everything had been changed. Where first here we have pairs connected to each other, okay, in series, in pairs connected in parallel over here. Okay, this is connected in parallel. So that's the main difference of phase variable, controller, canonical, and also the parallel form. Okay, I just show you all the types of state space form. However, in our course, as I mentioned earlier in the class, we only consider or we only tackle these two forms where you learn about how to draw a phase variable form or how to come up with a phase variable form of a state space model, and later on convert it into or maybe represent it in other form known as controller canonical form. Although there are other form that you will come across in most of the textbook, maybe you will come across to parallel, cascade, also observer canonical form. But in this case, we will not cover all these um, form. Okay, why? The big question is why cover only these two? In MATLAB, normally it will represent your state space model in the form of controller canonical form. And of course, this controller canonical form is very useful in order for you to design a controller. When you try to design a controller, normally you will use controller canonical form or phase variable form. It's easier. Um, in the sense that when we try to come up with a solution manually, maybe we would say parallel form is very useful, because parallel form we uh, write down our transfer function in a cascade. We cascaded our transfer function so that it's easier for us to find the solution manually, find the solution in time domain manually. But it's not that convenient as we think, because sometimes the value over here could be as I mentioned before this, it could be a, in the form of complex number, and sometimes maybe it also involve trigonometry element, so like cosine, something like that. So it's not as convenient as we think, but sometimes this parallel form is quite useful if the transfer function can be easily cascaded into a few elements. For example, like this, we have s to the power s plus 4, s plus 6. It's easy lah. If this is okay, if this denominator is more complex, meaning that a lot more to do lah for us to in order to convert into parallel form. And the last one is known as observer canonical form. Since we didn't cover about observer topic, I think maybe later on, if you get into your postgraduate studies, maybe you can have a look at the observer canonical form later on. But at the moment, I just would like to say that this observer canonical form is very useful in terms of designing an observer, especially when we talk about Kalman filter and so on. All right. Any questions so far? I think we are towards the end of our lecture today. Any question?
So for the parallel form, we not use, not you need to study, right?
Yes, of course. This okay. Maybe I should highlight the important form that you need to know.
I think you already circle, right? Only two is a phase variable and a controller, right?
Yeah, yes. These two, phase variable and also controller canonical form. And if you look at my example, basically my example only mention about phase variable and also controller canonical form. So that's two should be enough for our course. if you want to know more, maybe you can get into a postgraduate study lah. Okay, any question? And of course, if you get into the textbook, it will explain you about this parallel form, this cascade form, and it's good for your knowledge, especially if you are looking for a job involving control engineer, something like that. Maybe it's good lah. You know all these forms. Not, I think in terms of interview, maybe they would like to test your knowledge. Yeah, they try. What are the form of when we talk about state space representation? Maybe you can spell out lah. This we have various form, but in details, maybe you will know only these two forms at the moment. Later on, maybe you will try to enrich your knowledge from time to time. Okay. Any question?
No question for me, Doctor.
Terror ni.
Apa, Doctor?
Bun hebat ni.
Taklah. Tapi ada gunaan mental sikit, so boleh faham lah.
Okay.
Ada idea lah macam mana buat.
Okay. Anyway, we will meet again on Thursday. Okay, Thursday morning, and I hope that you finish up all the exercise. And if one of the student over here able to solve the question, I will show you my answer lah, the answer. So if no one submit it, or I mean no one try to share his or her answer, maybe I also not going to share my answer, the solution of the exercise. Okay, can we make a deal like that?
Yes, of course, Doctor.
Okay, all right. I think we will meet again later on Thursday. With that, I think that's all from me at the moment. We meet again this Thursday. Until that, everyone should take care of yourself, especially not only physical but also your mental health, your mental fitness as well. So hopefully everyone stay in a good shape. Thank you so much. See you again on Thursday.
Thank you, Doctor.
Okay, bye-bye.
Bye-bye.